Use augmented matrices and Gaussian elimination to solve the system x minus y plus 3z equals 4, x plus 2y minus 2z equals 10, and 3x minus y plus 5z equals 14. We're going to start by rewriting this system of equations as an augmented matrix that we can work with. The entries are going to be 1, -1, 3, 4, 1, 2, -2, 10, 3, -1, 5, and 14. And remember that when I'm dealing with augmented matrices and Gaussian elimination, I typically label the rows A, B, and C instead of talking about equation 1, equation 2, and equation 3. The reason I do this is because with a matrix, all of the entries are represented by numbers, so I think it makes sense to refer to the rows as letters to keep them separate. So remember that our goal with Gaussian elimination is to get these three entries to change to zeros by using row operations. So we're not going to do anything to the first row, which means we can just copy those numbers over to the next step. But what we want to do is we want to get rid of this 1, and then we want to get rid of this 3. To get rid of the 1, what we can do is we can take b minus a, because in that case, 1 minus 1 gives us 0. So the row operation we'll use here is b minus a. So we have 1 minus 1 is 0. Then 2 minus -1 is the same as 2 plus 1, which is 3. -2 minus 3 gives us -5. And 10 minus 4 gives us 6. All right. For the last row, C, to get rid of this 3, what we can do is we can multiply row A by 3 and then subtract row C. So that'll be 3A minus C. When we do that, 3 times 1 is 3, and 3 minus 3 gives us 0. Just a quick note, you could have done C minus 3A, or A minus B for the row above it, and you would still end up with zeros. You would just have the opposite of the other entries. There are generally multiple ways to choose row operations in Gaussian elimination, so it's possible that you might choose a slightly different order, but still get the same correct answer in the end. Anyways, we said we were going to do 3A minus C. We've already done that for the first column. Let's look at the next one. 3 times -1 is -3, and -3 minus -1 is the same as -3 plus 1, which is -2. Then 3 times 3 is 9, and 9 minus 5 is 4. And then 3 times 4 is 12, and 12 minus 14 is -2. All right. So we have gotten rid of 2 of the entries. We've turned them into zeros. We want to get this -2 to turn into a 0, but that's going to be a little bit complicated to do in a single step because 3 is not a multiple of -2 or positive 2. But one thing we can do is we can take this row and we can divide it by 2 to change this into -1, and that will make the next step easier. So we're going to take row C and we're going to divide it by 2. This leaves the first 2 rows unchanged, so we just copy the entries down below. And then the third row, when we divide by 2, becomes 0, -1, 2, and -1. Now, we still want to change this entry into a 0, but we're in a slightly better position to do that now. Here, we can take 3 times this last row, which would give us -3, and then we can add the second to last row to it, and that will give us 0. So we can replace row C with 3 times row C plus row B. Again, we're not doing anything to the first 2 rows, so we just copy those over. Then for the last one, we've got 3 times 0 plus 0 is still going to be 0. 3 times -1 is -3, plus 3 is 0. 3 times 2 is 6, plus -5 is 1. And 3 times -1 plus 6 gives us +3, because we've got -3 plus 6. All right. So from here, we can go through and we can use substitution to solve for x and y, because we know that z is 3. So when we translate these back into equations, this last one tells us z is 3. The next one tells us 3y minus 5z equals 6. And the first one, x minus y plus 3z equals 4. At this point, we should be able to go and use back substitution to solve for y and x. So we're going to substitute z equals 3 into the second equation. That gives us 3y minus 5 times 3 equals 6, which is 3y minus 15 equals 6. If we add 15 to both sides, that gives us 3y equals 21, and dividing by 3 gives us y equals 7. And then once we know the values for y and z, we can plug them into this first equation to solve for x. That gives us x minus y, which is 7, plus 3 times z, which is 3, equals 4. So we've got x minus 7 plus 9 equals 4. Combining these constant terms gives us x plus 2 equals 4. And when we subtract 2 from both sides, we get x equals 2. So we can write our solution x equals 2, y equals 7, and z equals 3. Or if we're asked to write them as an ordered triple, as coordinates, we can write this as 2, 7, 3. And that is our final answer.